Good morning to everyone. And Ernie has us listening to Bruce Springsteen. And what was your cut there, Ernie? My own town? My hometown. Okay, which for us is Modesto. And you could have done better in a selection of that and starting right at the time and something with a bit of passion or, I don't know. You're going to have to hold you accountable for that, Ernie. Okay, I've been given some feedback. And the feedback I've been given has to do with word problems. I need to get you a palm tree, Richie. A palm tree and an umbrella and maybe a Pepsi can or something, some sand there. Talk about laid back. Okay. Laid back. I don't know. Oh, you can pay attention better with the palm tree. For those of you who can't see, we've got Richie with sunglasses on, laid back in a chair, looking like he needs need an ocean beach in front of you. Okay, better not to be stressed in word problems. I think you're carrying this to an extreme, though. Carrying it to an extreme. Word problems. I've heard a lot of frustration. Let me make some just general comments about word problems. In algebra, pre-algebra, and beyond. Of all the things in an algebra class, word problems, more than any other one, usually cause some frustration. Just goes with the territory. And in a pre-algebra, maybe more than you'd have in an algebra class because it's very new in a pre-algebra. By the time you get into the Math 70, you've had some experiences with it, and it may not seem quite so bad, but it's still there. So the first thing I want you to understand, if you were frustrated last night, this morning, and feeling uncomfortable, expect it. The thing I liked that I heard, this made my morning good already. Falling to sleep with the book in hand, pencil in hand, way late in the morning, doing math. This is good. And staying up until 1 o'clock doing algebra problems. You make my heart warm. You make me feel good. That's the commitment. Now, understand, with that commitment and that hard work, it still may not feel comfortable, and that's okay. Just keep at it. Don't give up on it, and eventually it does get more comfortable. Now, some suggestions for this process. It may seem like the word problems go forever and never seem to be alike. Every one seems like a new problem. After a while, you'll be able to catalog them. You'll catalog them into problems about numbers, integers. That's a class of problems. There are problems about geometry, and those two classifications will stay there through 70 and 90. We do things with distance problems. We're going to do things with mixture problems, where we take two different saline solutions and try to combine them to get a new one. Those are ahead of us. So there's a limited number of types of problems. The key is to recognize it and have one or two that you've done that you know how you can do and feel comfortable about them. What I want to do today is nothing more than answer questions about problems you've tried. And not just give solutions, because that's not the intent. How do we think through them? What are we hunting for? And remember, there are 3 basic steps. Identify your variable. You'll see it always as let x equals. Write your equation and solve it. Those are the 3 steps. As one of you shared with me earlier, before we started our broadcast, if I can get the equation, I can do it. Getting that equation isn't so easy. One last comment. Whenever possible, draw a picture. Now, in some of these, pictures aren't helping a whole lot. But if you have a geometry problem, you do draw the picture. And I guess a comment, Michael, that you made, and that is you look at some of the problems involving like a perimeter or some information, and it seems like this isn't practical. I mean, I can't see how you would have a problem like this. To a degree, we are fabricating problems that may not have a practical kind of application. If I try to construct problems that force you to identify a variable and get an equation, and they don't seem quite as practical as you'd think, you have to give us a little bit of license for trying to create problems that can be done and using some geometry in the process. The idea that we do geometry in algebra, going back to Isaac's question, I think, from yesterday, yeah, there's a lot of geometry in the algebra course, and you need to understand that the curriculum has changed. At one time, between an algebra course and a second semester or second year of algebra, you took a geometry course. And when we do it here at the college, we go from the first semester of algebra to the second semester of algebra, making 2 years of algebra with no geometry in between. When you get done with like what's called a Math 90, which is our second level algebra or intermediate level algebra, and then you go into something like a pre-calculus or a statistics course or a finite course, the finite, the stat are in business majors. You could take a course in 101, which is sort of a liberal arts approach to mathematics. You can do other courses. All of them, in essence, assume or hope that you've had some geometry. And we don't have it in our curriculum any longer. So we pick it up in the algebra course, and that's why this author, and the same can be said for the Math 70 book, you're going to see geometry there so that you become familiar with the background. That's why in Math 10 I did formulas to try to provide that background. Isaac? Oh, okay. The question that's being asked, how much math do you end up to get a doctorate, and how high do you go? Just say it this way. You have 4 years to get a BA, 15 hours to 18 hours a semester, if you do it. Then you get a master's, which will be another 30 hours, which is at least another year, and you take nothing but math courses. Then you spend another 3 to 4 years for a doctorate taking more math courses, and it's going to depend on what you go ahead and focus on. So it's more a matter of just taking lots and lots of courses and lots of tests and pushing one at a time, just one after the other. And if somebody had said to you in kindergarten, how many courses are you going to have to take before you could get out of the 8th grade? You'd think, I'll never make it. Then you say, well, how many to get out of a credential or a diploma in the high school curriculum? And then you think, okay, what do I need to do for an associate degree? Just think of it of a lot of courses, each one comes after the other. And like taking one step at a time, eventually you've gone from here to LA or here to New York. But if you look at the whole thing at once, it's very intimidating. Okay? I'd say probably the biggest thing to answer your question, you have to be willing to work very hard, be very focused, very disciplined, and want it very badly. If you can do all those things and then be willing to spend 6, 7 years of your life doing it, then you do it. It's commitment. That wasn't one of the word problems we had, so let's go back to the word problems now. Now, some of you indicated you got through maybe 2 problems, 3 problems, and that was it, okay? So I guess we need to go back to those first problems and find out what it was that bothered us. For those of you with the book, whether you're with us here in the class or you're watching, remember we were talking about section 4.5. So give me a moment, Sandra, and I'll be with you. I first wanted to see what the first couple problems were and see what we're dealing with in terms of the exercises. Now you say the first couple problems. Remember, your 1, 2, and 3 are not the 1, 2, 3 in the text. So the first problem that's in the text was this kind of problem. This is in section 4.5 as we go to it. That's why I have it circled. And it says one number is 3 times another number. And it says the sum of the numbers happen to be 32. This was the version in the text, not the one you did on the computer. Now, I have a question for you as we come off there. What were you expected to provide in the computer solution? What steps? The solution itself, but you didn't have to put in the equation? Sometimes you had to put in the equation? Okay, so you write in the equation, and then you give your answer. 2 steps? Depends on the problem. Okay. What I want to see in your documentation is an equation, the variable, and your answers. Minimum. 3 steps. What x equals, the equation you had, and if necessary, intermediate steps. Fair enough? Now, in terms of the first 2 problems, which should have dealt with, at least from what I'm reading here, one of them should have involved working with integers. What was the first problem that you did if you had trouble with it? Anybody have a problem with the first one you want to discuss? No, I'm talking about the first one in your set. No problems with the integer problem then. Okay, I'm on page 279, and I'm looking at number 9, which was my first selection that I made on the computer. You should have had a problem similar to that for your first problem. Was there a difficulty with that first type of problem? Isaac? Okay. Let's look at this one again one more time. There are 2 numbers involved. This is number 9. This is in section 4.5. And it says you have 2 numbers involved. So as we go to the board, I'm going to let x equal my first number. Now the way the problem's written here, it says that the second number is 3 times the first. Is that right? 1 first is 3 times another. So if x is the first, 3x is your second. Now that is the most critical part of the problem. Because the next statement is what? Go back to the problem. It says that what? Well, no. The next critical statement is the second line. And you see the phrase, the sum is 32. Now, as I go to the board, some authors expect you to write a verbal statement. Sum equals 32. But the sum tells you you're adding. And your 2 numbers are x and 3x. So I replaced the sum, just like parentheses, x and 3x is that sum. That is equal to 32. There is your equation. So this is the first critical step. This is your second critical step. Now I could argue, and I would say I would like to see an intermediate step. I'd like to see that you have 4x, that you simplify that side, and then I'm satisfied at that point if you will say 8 for your solution, but you have not given me an answer to the question. What are the 2 numbers? Find the numbers. And so you still have an obligation to tell me that your numbers are 8 and 24. Now that would be a full solution. Okay, Jessica, did you have a question or?
Yeah, but I'm not sure.
Okay, while you're thinking, Michael?
Do you want to see another intermediate step?
No, I'd be happy with that. I wouldn't be quite so happy if you said this and this. I think there's an intermediate step that really is important there. James? That's fine. 3x plus x or x plus 3x because of commutativity. The sum of the 2 numbers, and sum can be reversed, so I'd have no problem with that. But I'd like to see one intermediate step here, ideally. If on a test you did this and you said x is 8 and 24, I'd accept it. But for what you're doing right now, these steps I think are important. Jessica?
Oh, no, I thought it was one where it has 24 times, but I know it's 3 times 8 is 24.
Yes, 3 times the other. There was one number is 3 more than another. 3 times, didn't say that right. 3 times another, not 3 more than another.
Okay.
Richie? I have an 8, and the other number is 3 times 8. My second number is 3 times as much. So if the first one is 8, which is what I found, then I just substituted in here and said 24. Make sense? Okay. Anybody else there? Now, your first problem, was it very similar to this? How many of you had a problem like this for the first problem in your computer? See your hands. Okay, so the computer's doing what it should. Give you a problem like this instead of changing it totally. That's my concern. That I chose this one because it had integers and it gave you something with geometry. I feel very upset about that. This is a classification of problems. If you had success here, then in a way you've got 33% of what the goal would be from my point of view. That you can do 3 different kinds of word problems. You've got 1 out of 3. That's pretty darn good. Now, if we can just get 1 more and get 2 out of 3 today, then that's good. You only have 1 more to go. Geometry problems. Let's just look at a typical one. And remember, no picture here. But in geometry problems, draw me the picture. Sort of like in Jerry Maguire, show me the money. Okay, same idea. Draw me the picture. Which one would you like to look at, Sandra?
On page 280, number 17.
280. Ah, interesting looking diagram. Okay, a balancing act, right? We've got a triangle. What kind of triangle is that? Equilateral. Equilateral. Okay, and it's balanced on a rectangle. Okay, fascinating. I have no idea where they're going with this. They say it's a corporate logo. Okay. It says it is an equilateral triangle sitting atop a rectangle. Atop. Interesting twist of phrase. Instead of on top, atop. But at any rate, we are told something about the sides of the triangle being equal in length to the length of the what? To the rectangle. So let me slide over. What it's saying is that these sides, if you took this triangle and just laid it on top of the rectangle, on its base, then it looked like a house. This is what happens to a house in a tornado. The roof is lifted off and dropped back down, point down. But again, rotate, meaning like a clock, rotate it, and this base would be the same here. Is that what I'm reading? Okay. Now it says that the perimeter of the triangle is equal to the perimeter of the rectangle. That's interesting. So the perimeter, these 3 sides here, are each of the same length. That is equal to that. So what does it say about these 2? Well, they're the same, and furthermore, they have to be what? Half of the triangle. One more time. If these 3 sides are the same as the length of this rectangle, I've got 2 of these sides is equal to what? These 2. Now the perimeter of the rectangle includes what? 2 pieces here. Since the perimeter must be the same, it's 3 of these lengths. These 2 together have to be 1 of those lengths. Sandra, your eyes tell me that's not going across.
Wouldn't it? So it wouldn't be half then if it was only one of the lengths.
The width is half the length. If 2 parts will make the whole, each one's half of the whole. I still don't know what I'm supposed to do here, but I'm supposed to find this length, correct? What it would be if I have something else. Is there anything else? The width of the rectangle is 10 feet less than 3 times the length. The width of the rectangle, so I know what the width is, and it's half, by the way, of the sides of the triangle. But I know that the width, so let me come back to that statement so we can see it. I think this is enough to see here. The width of the rectangle is 10 feet less than, meaning you're going to subtract the 10, correct? From 3 times the length. That's the statement I want. So let's see what we can do. Let's let x equal what? The length. So we've done that. Now, if I take x is the length of each side of the triangle, it's also the length of the rectangle, so I'm just going to call it length. Then the width is going to be 3x minus 10. Is that correct? 10 less than 3 times the length is the width. Okay? Now that information is given to me. And I know that 3x is going to be the perimeter of the triangle. So I could, if you want, this kind of a written statement, I could have said perimeter of triangle is to equal the perimeter of the rectangle. Perimeter of the triangle is 3x. Now, the perimeter of the rectangle is 2 times x, because I have 2 of the lengths, plus 2 times what? The width. Now, this 2x didn't read so well. Now, that, in essence, whether you look at this as an equation, I think this step right here, getting the expression for the perimeter of the rectangle, is straight out of yesterday. The difference would be that I'd have to tell you in this rectangle that I would draw. Let me illustrate that to this extent. Let me just draw quickly a rectangle. So if I have the rectangle and this becomes x, then on my rectangle, I have to understand this is 3x minus 10. I could have just drawn that picture for you. And then say, get me the perimeter of that rectangle. And you would have to say, it's 2 times the length plus 2 times the width. And that would be your expression for the perimeter. Now, the fact that the perimeter of the triangle and the perimeter of the rectangle are the same allow you to get the equation. Now, if we get to this point, we should be home free. The hard part is, does it make sense how I'm getting to that equation? And Sandra, where are you having trouble? Let's come back down to here. If I gave that picture to you, no, but I'm going to ask this question. If I just gave this to you and ask you to find the perimeter of the rectangle, would you agree you get this up here? Because this is x, and this is 3x minus 10. And so I'm just going to go for a walk. That's x plus this, plus this, plus this, which just means double the length, double your width. That's the perimeter.
So where did you get the 2, right in front of the open side?
2 of these sides, right?
Oh, okay.
Going for your walk. So if you didn't want to do it this way, you could have said that that perimeter is x plus 3x minus 10 plus x plus 3x minus 10. That's your perimeter of that rectangle, correct? Or you could say, well, it's really twice the width plus twice the length. Going back to Math 10, we said if you have a perimeter of a rectangle, our formula, I believe, was 2L plus 2W, correct? That's what I did here, knowing that x was the length and that this 3x minus 10 is the width. Is that part okay? Now, that was for this rectangle. I'm going to slide over just a little bit, Ernie, and I'm going to create what I hope is an equilateral triangle. Now watch what I'm doing. I'm going to make an arc. Need to get more chalk. Sometimes when you want chalk, you have it, and other times you don't. Okay, there's one arc. I don't know if that's coming across. Then leaving my hand the same way it is, bring the other arc up, and they meet right here. Now that's going to create, when I join those points, an equilateral triangle. And that's called a construction in geometry. Now, if I'd done the same thing down here, I'd have an equilateral in the bottom, correct? If I would join those 2 points, the line joining these 2 vertices would cut this base exactly in half. It would be called the perpendicular bisector. So one more time. Okay, I have this length. Create an arc, then come over here, same length, create an arc, but do it down below the same way now, without twisting my hand too badly. These met down here, so I have another vertex down. I can make another equilateral triangle, but if I do this, this line I happen to get is at 90 degrees to the base. It cuts the base into 2 equal parts and happens to be the altitude of the triangle. It's not needed in this problem, but it's just additional information. A construction called ruler and compass constructions out of geometry. Okay, if I tell you that this is x here, and this is x here, and this is x here, for Sandra, what would be the perimeter? Oh, okay. And you just told me the perimeter for this one was this, correct? And what did the statement say? The perimeter of one is equal to the perimeter of the other, so I put an equal sign and you have your equation. Now are you okay?
Can you show me? Put the equal sign and have the equation.
Equal sign?
So that's the answer?
That's my equation. I have to solve it now, but I need the equation first. This was the first critical step. Now I wanted to make sure you understood where I got the equation from. Now if you're happy there, I've got you happy temporarily. Okay, well we'll go for temporary happiness. Does anybody else have a problem with how I got this equation in this particular problem? Now we make a very naive assumption. I say we in academia make a very naive assumption. Now that we have equations, we can solve them. I remember last week's quiz. We had equations. Were we always able to solve them? Why? Usually some little trap. Where's the trap in this problem? There will be the trap. Because you have to use the distributive property and take 2 times the 3x and 2 times the negative 10. And if you don't pick up that negative sign, even though you've got the best equation in the world, you won't get the right answer. Michael.
I got that equation, but I wrote it different. I didn't put the 2 times, I just wrote it out.
You did like I have here. That's acceptable. This is better, but that's acceptable. I hope you can see why this is more compact. I didn't have to write out as much. And mathematicians in some ways, and I say this with some humor, given that answering Isaac's question, what do you have to do to keep getting degrees, and then to say a mathematician's lazy. Lazy in a way that they want to make as few steps as possible. They want to have as short of an expression as possible, and to try to reduce the amount of garbage in a problem. And we call that paucity. Like paucity. Paucity. And the idea is you have as few symbols as you can have. You try to have as few words as you can have, and as few lines as you have, and still be understood. So this is what I mean by being lazy. Okay? They're also, to get the kind of degree that Isaac was referring to, you have to have a degree of stubbornness, commitment, unwilling to give up, nearly obsessive about getting the degree, because it would be awfully easy just to say, I'll quit. You got to want it very, very badly. And then you put in the effort to do it. And it's just one step in front of the other. Okay? So, what are we going to do at this step? From here, I'm going to get myself a new expression on the right side. Now remember, to simplify, sometimes you have to do what? Make it look a little bit worse. So, in a sense, Michael, with what you did, you just had to simplify directly, and you got the same result at that point. I still need to do what on the right side? Combine these two, 8x minus 20, and if Michael down here had taken this, he would have had his 8x minus 20 without having to multiply. So, yeah, 6 of one, half the other. Okay? Meaning half a dozen versus 6. That's 3x. Now, this is the dilemma. What do you do? What's your choice? And we talked about this yesterday. There is no right answer here. I can tell you my preference. I like to get a positive coefficient. I like to recommend that to my students because it's the minus signs that'll mess you up sometimes if you aren't careful. So I'll subtract 3x from both sides. That'll give me 5x over here. And I will add 20 to both sides, which gives me a 20 here, and I'm there. Finally, 4 is equal to x, or x is equal to 4, correct? Now, if you're asked for the dimensions of each shape, my equilateral triangle is 4 units on each side. When I look at the rectangle, 3 times 4, and this gets back, I think, Richie, to your question now, because I want this other dimension. This 3x minus 10 is going to be 3 times 4. You don't want to put an x for. Just substitute. So 3x is 3 times 4 minus 10. That'll come out 12 minus 10 for what? A 2. So you have a 2 by 4 rectangle. Okay? It's also called a piece of wood. Okay? And it's what I've threatened to hit some of you up the side of the head with in certain occasions. Any further discussion? This problem. Now, Sandra, are you happy with the solution?
Happy with it. It's so much that it's just like.
This is overload with symbols?
Well, it's just that, for me, I could see it's definitely somewhere between there.
Well, good. That's my...
It's still kind of hard.
Okay, so people can hear what you're saying because all they're seeing is my reaction. You're saying, I make it look easy, but it can get hard. Yes. My goal is to make it seem to you, hey, that's easy. You have to realize that when you do it on your own, you're going to say, that's hard. It goes with the territory. How do you make it to where you can say, it's easy? Well, try explaining the problem to somebody else. Now, you can make enemies this way. You've got a close friend, say, look, I want to explain this algebra problem to you. And they say, I don't want to listen to you. And you say, I want you to do it anyway. This is where I recommend the refrigerator door. Explain it to the refrigerator door, Sandra, late at night at that 11 to midnight time when the kids are asleep, you've got time, and you're wide awake. Yeah, right. But if you talk out loud to the refrigerator and nobody else is around, this is good. You explain just like I'm trying to explain. The best way you'll learn anything is to tutor it. Tutor it. Explain it to somebody else. That's when you learn. And I didn't understand that until I, by accident, had to do what we would call tutoring. And that was because somebody found out I was a math major, and they decided that they found somebody that could answer questions. And so living in a dorm with a few hundred people in there and only 2 math majors, it was a constant. What? When you say made it a choice?
They made a good choice.
Well, I don't know about that. At the time, I wasn't sure I could explain some things. But that's where I learned that I didn't know what I thought I knew, because I just did things because I was told how to do them. When I had to explain them and somebody say, well, how did you get that? Or could I do this? Then I started an understanding. But that's where it came from. Michael?
Did you charge them?
No. Question was, did I charge them? I didn't have no thought of that came at the time because we were in a dorm and I figured fair play, you asked me about this, I got some questions too. Because I was taking other courses that I had questions in. And so it was a trade. It was sort of what we would call bartering. Okay, I'll answer your algebra questions, but I have a question about the philosophy class or the literature class or the class in psychology. I was taking a course in psychology where we were spending time looking at the various forms of psychology, behavioral modification with Skinner, and we were looking at neuroses and psychoses, and I thought I had all of them when you study them. Anybody taking a psych class thinks they got every one of the problems that are possible. And so it was a trade-off. I gained more than they did is what's frightening in the end, because I understood and they oftentimes still didn't. My comfort level with word problems really occurred when I had to explain them. That's what you need to understand. Now, you say, okay, I've got that one, but every one of them's different. Not one of them's like the other. Yeah, they are. Draw pictures and translate. I said yesterday, don't try to do a problem until you can what? Understand it or say it without referring to the book. It's got to be your problem. Back to Sandra's 11 to midnight free hour. During the day, you read the problems so that you've had 10 hours to reflect on them before your free hour at 11 to midnight. And if you think about them all day and they keep bugging you, by the time you're able to look at them, some insights, those moments of light bulbs going off. Because if you paint yourself in that proverbial corner, it's 11 o'clock and I've got to be in bed by 1, or I won't make it up at 6, and you don't see something, then you have no time to put the pieces together. But you start that problem at 11 o'clock today, and by 11 o'clock tonight, 12 hours of worrying about it, and put it in a 3x5 card if you're just down to one problem that's bugging you. Read it 15 times between now and then. Then come back and look at it. Let your subconscious work for you. Okay, that was the second kind of problem. Now, is there another one that we can look at? Okay, Tabitha, I'll go with yours first. Number 25. So I'm coming back. And a lot of what I'm saying today has to do with emotions, attitudes, approach, more than algebra. But that's what this is about. Because there's no magic where you can just say, I can do these, until you've suffered a lot. That doesn't make you want to be a masochist, but 25. 25 is different because we're dealing with what? Angles. Now, is that diagram go with this problem or not? No, but that's an interesting problem. Let's do some physics. You have a light ray coming in on a mirror at a certain angle. It bounces off so that these two angles are the same. When you reflect, you come in at an angle, it bounces off, so these two angles are the same. And all totaled, these three angles have to be what? 180, because it's called a straight angle. These three angles, in essence, must total 180. Okay. Interestingly, as I go to 25, I'm dealing with what? A triangle, right? And I'm told that the sums of the degrees in a triangle will give me what? 180 again. That's sort of neat. So I have the sum of the angle measurements. The measurement of an angle must be 180. Now it tells you that one of the angles is 43. Well, that's nice of them. I'm not going to go any further. I'm going to draw a triangle. Now, what kind of triangles are we talking about? Yesterday we had some language. What were the triangles as I go to the board? What types? Okay, we had an equilateral. Okay, and then an isosceles. Isosceles. And then? Well, that one was the right triangle. A right triangle. Angles are congruent, but they aren't triangles. So I have a right-angled triangle. And then the last one. No, the angles are congruent. This was not in your book. Supplementary means the two angles add up to 180. Scalene. Saline, saline, over the ocean blue. Scalene, scalene, until the problem's done. Scalene triangles. Just remember raylene. Okay? If you call Raylene Scalene, she's going to have my head this afternoon, right? So don't, but, Erica, don't go there. My name will be mud before the day is out. Okay, scalene triangles. So we don't want to have the sides equal. We don't want a 90-degree angle. We just want a good old triangle. So I do a side there, and I do a side maybe like that, something like this. And I've got to be careful that I don't what? Get a 90-degree angle, and I think I'll do something like maybe this. Okay, I don't think the sides are the same, and I think that that's scalene. Now, you don't need the antenna on it. That better? Okay. One of the angles is 43. Which one could it be? The little one. Could it be this one? No, it can't. Why can't it be that big one? If I think of a perpendicular here, that would be 90, and so I have more than 90, and 43 is smaller, so it can't be that big one. Now, could it be this one or this one? Be careful. Again, that one. No, it's that one. No, it's that one. 90 degrees, right? Okay. I've got a little box there. Thank you. A 45 is half of a 90. Okay, 43 is very close to 45. Could it be that little? No. Thank you. This one seems like a better candidate for 43. Now, is it critical that I put the angle in the right spot? Not really. I should make that 43 bigger. I don't mean make it 48, but make it a bigger set of digits. And that's not the temperature. There are 360 degrees in a revolution of the clock, so we measure in terms of degrees right now. Later on, we won't. This is degree measurement. Later on, you'll do radians. Okay. Now, so far I've done nothing but have fun. I've drawn a picture, and now I need some information. So let's go back to the problem. We have one of the angles is 43 degrees. Now, it tells me something about the other two angles, doesn't it? The second one is 2 more than twice the measure of the third. 2 more than twice the measure of the third. So I would suspect if I call this one X, the small one, then the other is 2 more than what?
X.
Let's go back and look at the statement. 2 more than twice the measure of the other. Translation. That's the key to the problem. You get there, you should be home free. Let the good times roll. Because what must you know? The sum of the 3 angles is 180. So the sum of the 3 angles is 180. There's your verbal statement. So that's X plus 43 plus 2X plus 2 is equal to 180. Equations there, the rest should fall in place. Again, if I had to give you a recommendation, it's one I did in the doctoral program when I first started doing it. Find a room with a blackboard. Go to the blackboard with the chalk, draw pictures, get a couple of you together, and try to explain and discuss verbally what we are doing just now. You do it. Because as you hear it and you have large motor movements on the board, it will stay better with you than working in silence on your own with a piece of paper and a pencil and a straight edge getting frustrated. It works, folks. It works very well. For those of you who are getting together in the evening, fantastic idea. Okay? It's the difference. Just keep doing it, and it starts clicking. And there is a comfort zone that'll get there. Okay? Another type of problem that you fought. Anybody get further where there was another type of one? Tabitha. Oh, we got there. You got the hard part. The other part's supposed to be the easy part. Let's see what happens. Tabitha's saying, I got there. In a test, I would give you 7 out of 10 points for where you got. Because you got the setup right. You got the equation right. Did you draw your picture? Okay. Without the picture, 2 points off. But with the picture, the variable, I should have said somewhere, let x equal, I'll just say, an angle of the triangle. So an angle of, and then just draw a little triangle. Okay, let's combine. What do we have on the left side when I combine? How about 3x? An x and 2x is 3x? Okay, so 3x plus 45 equals 180. That okay? Now, once you get there, you don't want the 45 where it is. So I'll subtract 45 from both sides and get 3x is equal to 135. And then I remember from Math 10 that if I add the digits, 1, 3, and 5, I get 9. So 3 will go into that number. So 3 into that will give me 45. And so I had a 45 here and a 45 here, and therefore it happened to be, okay, isosceles. If the base angles are the same, that means you have to have an isosceles triangle. So it was a 45, 45, 43. If the sides are the same, the base angles will be equal. If the base angles are equal, it will be isosceles.
Those are the base angles?
We call it the base angles of, let's say I have a triangle that looks like this for the moment. These are called the base angles because this was the base of the triangle, and so we're saying these two are the same. So we draw a little curve and a little hash mark across it, and we say those are congruent angles. Since you have both of them, we're 45. Oh, hold it. I just made a DAE. I was thinking this was going to be complementary to here. I forgot that this was 43, so I am in error because I should find the measures. This was 43, this was 45. Then this is going to be 92, and I was thinking I had a 90 there, which is why I was going to go for a 45 isosceles right triangle. I don't. I'm at 92, 43, and 45, so I nearly got trapped. I did get trapped. But nonetheless, if I have two angles down here equal, the sides would be equal. Okay? Now, are there any other questions on a different kind of problem? Did you get that far where you had to deal with something besides the integers and the geometry? So we didn't get that far. What now, James? Yeah, the ones with the tables and such. Okay, so Michael, you're saying do another geometry one? Do you have a particular one, Michael, you'd like to look at? 24. 24. Okay, this is sophisticated pool called billiards. Now the argument, just like the mirror reflection, if you come in at a certain angle, you're going to reflect off at a certain angle. So these two angles here are going to be the same I'm pointing to. They're going to be congruent. Okay? Now, that's assuming you had light and you didn't put spin in the ball. Okay, so this is playing a straight shot, no spin. Banking it off the side of the table. But now we have a little bit of a caveat here, right? A little wrinkle. Because you're going to do what? Side spin. You've done that with ping pong. Coming off there. Ever hit a ping pong and you come down slice underneath the ball and it hits and instead of going right there, it goes like that and then you win the point and make somebody up. Yeah, you come up over the top or slice underneath and the person you're playing against thinks you're evil. It's best not to do this with anybody you have a close relationship to. Okay? Because they will get angry. Why did you do that? I wanted to win. Doesn't go well. Sarah and I do not play ping pong together. Okay, we deflect. Now notice, 6 degrees less than what? The angle formed, the initial angle. So if I look at this coming back to the diagram, if I look at coming in here, this is the initial angle, right? But this angle here will be what? 6 degrees less than that. So if it's less, it's actually going to come off this way more because of the spin. I think you can picture that. So if this is x, this angle is going to be what? X minus 6. Now, we need some other information, correct? Because we know that the total of these three must be what? 180. So I need something else. Now, it tells me the measure of the angle formed between the initial and the deflected lines, that's this angle I'm pointing to, is what? 10 more than twice the measure of that initial. So this is 2x plus 10 here. So if I'm just looking at that diagram, pencil that's got fine lead in it. Okay, who can I reach closer? Ouch, that's got fine lead in it. Okay, this is x. And so this is going to be what? No, this one's x minus 6. And this is 2x plus 10. Because this was to be 10 more than the original angle. So I have 2x plus 10. So what's the total of all this mess? 180. And that is exactly what you have here. Instead of x, using a for angle, which I'm not impressed with. But there's the little angle. Here's your middle angle. Here's the third angle. And you add those together and you get 180. And then it is supposedly home free. So, Ernie, as we come off there, I hope that helps. Leaving this open again tonight. If it doesn't, you work at it. You fight it. You keep plugging away. Get in a group. Don't give up. I feel like I'm giving the halftime statement to a football team, and you're down 40 zip. Ernie, what is our close going to be? I hope you chose